Now we will start to discuss quantum harmonic oscillator, and we will start from the formulation of the Hamiltonian that we derived in one of the previous videos. It's a form of the classical Hamiltonian of the harmonic oscillator, which is expressed in terms of dimensionless coordinate and dimensionless impulse. And the little drawback of this formulation is that here the representation of the operators will look somewhat different. So what is normally taught is that P is something like minus I h bar, and now partial derivative or spatial derivative of the corresponding Q. So this is the Q representation, coordinate representation of the momentum or impulse operator. Now this is not true in this case because we are using dimensionless P and dimensionless Q, so this is not the case here. It's not that say something wrong with it, but there is here is a constant which has some dimension, and this is dimensionless. This is also supposed to be dimensionless, so quite obviously it will be different. We will get rid of this, so this does not work here, and we will have a different definition. The operator P will be simply minus I and the derivative. This is easier. I mean, you can think that you are working, let's say, in case where the h bar in such units that h bar is 1 or something like that. Okay, so this is our this is our operator expression for the momentum, and this is the Q. And the quantum mechanical Hamiltonian that we will be using from now on, it's an operator. That's the way we quantize things. We just say they are operators. Here we will have, therefore, okay, I write it first like this, and now in this Q representation, the operator Q, the coordinate operator, is simply the Q itself. Okay, so we can actually say that this is now h bar omega divided by 2, and here we have minus second derivative according to Q plus Q square. So this is a coordinate representation of Hamiltonian. I was always kind of saying that, you know, this wave function or coordinate representation is just a special case, but that's precisely what we want here. We want to discuss the dynamics of this quantum harmonic oscillator in space. We want to see something that is physically appealing, and that will be the motion of the harmonic oscillator in space. So what shall we expect? So we have this harmonic potential here, and we would expect that this harmonic oscillator behave at least somewhat similar to a classical oscillator. So if I would put a ball down here, nothing is going to happen. So this is the quantum, the classical case of the lowest energy state. The similar occurs when we start with the wave function of the harmonic oscillator in the ground state. So this is the ground state. And one can see that the solution of Schrödinger equation with this Hamiltonian is actually a Gaussian function. So there's a distribution of probability of finding my ball down here, and nothing happens. Now if I want to get some dynamics, I'll basically shift the ball here and let it run. So it's gonna do movement like this, up and down. If I draw this in energy and not in the potential energy diagram, so if I would put E here, the total energy given by the classical Hamiltonian or expectation value of the Hamiltonian, and because this is a conservative system, that there's no friction here yet, I should properly draw the motion like this. So this green will be the motion. So the motion will be there and back, there and back. The ball goes up and down physically in space, but its total energy gets conserved. So in fact I have running of the stuff here. To this, in quantum mechanics, corresponds the case that I start with the same distribution, the sort of same state, but I just also take it and move it up here. So I'll create a wave packet here, and that wave packet, in the case of harmonic oscillator, is going to run back and forth also without the change of its appearance. Basically, the shape of this distribution given by the wave function in case of the harmonic oscillator remains the same. That's a very good approximation of the classical motion, because I could say, let's say, well, what about this distribution has a center of gravity or whatever, that's where my ball sits, and everything else is some sort of a quantum mechanical uncertainty. Yes, it really works like this for the harmonic oscillator, and that's where it stops. In all other potentials or other cases in nature, quantum mechanics gives results that are not so easily reconcilable with classical mechanics. In case of harmonic oscillator, you can say that, well, nothing has changed except of the fact that I have some distribution of the probability. There is still a ball which runs back and forth. We will also show other cases which don't have such a nice classical correspondence, but they will only appear once we start to introduce dissipation in the system. Once harmonic oscillator is a closed system, it has very close resemblance to classical system. So how shall we now get this? Our task now will be to derive some expressions for this shifted wave function. So shifted wave function will be our initial state, otherwise we would not see any nice dynamics. So shifted wave function. I mean, to be more precise, we have some psi 0q here. This is the wave function of the ground state, and we want to shift it. So we want to make out of it psi 0q. In this case, it's minus some q0, where q0 is this distance. So this is q equal to 0, and here we have q0 shift. Alright, we want to express this, and we don't want to, this is all nicely appealing to see it moving in space, and we will make a little video with wave packets moving in the space. But in fact, to calculate something in quantum mechanics, is always best to find some representation which represents this whole problem with as little elements as possible. So if you want to have a wave function represented here, you would have to discretize the space and calculate with discrete spatial derivative and so on. This is nonsense. Actually, it doesn't bring anything nice, and it's just a nuisance. You never know whether you are correct or not. But you also know, or we know from somewhere, that this harmonic oscillator can be represented in terms of the eigenstates of the Hamiltonian, and there is there's an infinite number of them. But if the shift is not big, that's what I can kind of say, and you have to believe me. If the shift is not very big, there is only a relatively small number of levels that has to be used to represent this dynamics, and with that limited number of levels, we actually turn again everything into an algebraic problem, a matrix, let's say a matrix 10 by 10, and in that case we again can solve easily the dynamics. Once we are done with the dynamics, we will just express this moving wave packet here in terms of an expansion of the wave function in terms of the representation of these states in space. So we will let's say have 8 or 10 lowest states of the harmonic oscillator, and for them we will need to know how the psi n q looks like. And with that knowledge, we will already be able to represent the result. So I'm talking about the future, and that future will come, or will start to materialize in the next video.